Well, let's continue on with double integrals. We're going to do a bunch more examples, and we're going to also look at doing double integrals in other coordinate systems, which is sometimes very handy. So let's look at another example. Any questions before I get started? Comments? Tutorials are still going? We have another quiz this weekend, so you can do that as soon as Thursday midnight until Saturday midnight, quiz 3. All right. Okay, if there's no questions, we'll just dive right in. So we are given a double integral. Okay, we're given this double integral, and we're asked to write the equivalent integral if we switch the order of integration. Okay, for all the functions we're dealing with in this course, we can switch the order of integration, we should get the same result. So that's what we're asked to do here. We're not asked to actually solve the integral. So let's just look at this double integral first, just to remind ourselves how these things work. Right, the inner integral is an integral with respect to y, which means when we do this inner integral and we do the inner integral first, we treat x's as constants. Okay? And so you hold x constant and you integrate in the y direction. That's what we're doing in this inner integral. Consequently, the limits for that inner integral could be functions of x. Okay? Or they could be numbers. That's your only two choices. They could be numbers or functions of x. If we're integrating with respect to y, they cannot be functions of y. That would make no sense. Because after we do this inner integral, we've integrated out y. Y is gone. Okay, so these cannot be functions of y, but they could be functions of x. One could be a function of x, the other one could be a number, or vice versa. After we've done the inner integral, we then do the outer integral, which is an integral with respect to x. Okay? There are no more y's, so we don't have to worry about holding y constant. Y has been integrated out, it's gone. All we're left with after we've done this integral is an expression of x. And we take the integral with respect to x, where x goes from 0 to 2. This is a definite integral, which means these outer limits must be always numbers, so that the final result you get is a number. Okay? Okay, well, if we're going to reverse the order of integration, that means we're going to, this same function is going to be integrated, but it's now going to be read dx dy, which means our limits have to change. And that's usually the hard part of writing a double integral, is figuring out what these limits are. So we're going to change the order of integration. Dx, we want to write this now. 4x plus 2 dx dy. And what are the limits? Well, we need to know the region of integration for that. And we can get that from the first integral that we're given. The region of integration is in the xy plane. Okay? The x limits are easy, 0 to 2. Okay, well that's easy. Here's 0 and here's x equal to 2. The y limits are functions of x. Okay, so that means in the inner integral here, y goes from x squared to y goes to 2x. So that means one of the boundaries for our region are y is equal to x squared, which is a parabola. Y is equal to x squared looks something like that. Okay, I get that from this lower limit here, because we're taking the integral with respect to y here. Okay, which means once we've taken the integral of 4x plus 2 with respect to y, we're going to have some function of x and y. The x's are constants. The y's I'm going to replace with x squared and 2x, which means y goes from x squared, y is equal to x squared, to y equal to 2x. Okay, well, y equal to 2x is a straight line that looks, I better get it right, it's going to look like this. Okay, that's y is equal to 2x. So that means my region of integration is this. Okay, any questions how I got that? Which means when we're writing this first integral here, we determine these limits here by drawing a arrow through the region of integration in the y direction, because in this first double integral, we are integrating with respect to y first. So we hold x constant at some x value, and we go in the direction of y. We're integrating in the y direction. This line enters the region at y equal to x squared. That gives me y min. And it leaves at y equal to 2x. That gives me y max. Now we're going to do the opposite order, though. We're going to integrate in the x direction, which means we hold y fixed, which means we're going to draw a line through our region of integration in the x direction at a fixed value of y. And we ask, okay, at what x value does this arrow first enter the region of integration? Well, it's along this boundary, which is y is equal to 2x, or x is equal to y over 2, right? If I rewrite this equation, it's x is equal to y over 2. So everywhere along this straight line, x is equal to y over 2. So this x value, where this line enters the region, is going to depend on where I am y. It's y over 2. Okay? So that means x min is y over 2. This arrow leaves at an x value dictated by this parabola. Okay? I can rewrite this equation, solve it for x. I get x is equal to the square root of y. I would choose positive square root of y because I know I'm in the first quadrant. I would not choose negative square root of y. Okay, so that value is going to give me x max. X min is dictated by this straight line, x max is dictated by the parabola. Square root of y. Okay, now I'm going to go, now I need the limits for y. Well, the limits for y are going to be where this horizontal arrow first touches the region of integration, which is right there, to where it just leaves the region of integration, which is right there, right? I sweep that line from here up to there. I go sweep through the region of integration, and I ask, okay, what value of y do I get here? Well, that's obviously y equal to 0. And what's the value of y here? Well, we know this is x is equal to 2. Y equal to x squared, y equal to 2x means this. You can solve these two equations for each other to see where this integration, or this intersection point is, right? It's at a value of 2, and this would be 4. Right? When x is equal to 2, y is equal to 4. Same thing here. When x is equal to 2, y is equal to 4. So that's the intersection point. So that means y max is going to be 4. Okay, so those two integrals will be equivalent. If you solve both of them, you should get the same answer. Any questions on how I got that? Again, sketching the region of integration is critical. I don't know how you can do double integrals if you don't do it, unless the region of integration is really simple. You know, it's a square or a rectangle. But any other type of curves bounding these regions, you got to sketch it. Okay, let's look at another example. We've got a function z is equal to a function of xy, which is y squared. And our region of integration is going to be x squared plus y squared less than equal to 1, x greater than equal to 0, y greater than equal to 0. Another hard part of doing double integrals is if you're not given a picture, figuring out what that region of integration looks like, right? And then once you got it, you got to find the limits. So this region is bounded by three things. The first one is the circle x squared plus y squared equal to 1. Okay, there's the circle x squared plus y squared equal to 1. It says x squared plus y squared less than or equal to 1. So that means the region of integration is inside of this circle. Okay, the second equation we're given is x is greater than or equal to 0. Well, that means we're looking at this half of the circle. And we're also told that y has to be greater than or equal to 0, which is the top half of the circle. So the only part of that circle that satisfies both of these is this first quadrant. So our region of integration is going to be this first quadrant of the circle. Okay, so we know that so far. The function we're integrating is equal to y squared. Okay, it's completely independent of the region of integration, right? There's two things going on. There's the function you're integrating, which is y squared, and then there's the region over which you're integrating, which is going to be this quarter of this circle. Okay, so we can do the same thing. We can set up our integral. So it's just going to be y squared and, I don't know, let's go dx dy. We'll integrate with respect to x first. Oh, no, let's do it the other way around is what's done in the notes. So let's do it the other way around. Let's do it with respect to y first. So dy dx doesn't really matter in this case because it's a symmetrical region. Okay, so what are going to be the limits? Well, we're going to integrate in the y direction first, which means we hold x constant. Okay, let's choose an x value right there. And let's keep x constant and integrate in the y direction. Okay, we're integrating in the y direction, so we're looking for y min and y max as that arrow goes through that region of integration. Well, y min is the value of y where it first enters, which is obviously 0. And it doesn't matter where I draw this line through the region of integration, y min will always be 0, correct? Because this is a straight boundary on this region. So y min is always 0. It's not a function of x. Doesn't matter what x value I draw that arrow at, y min is 0. However, y max will be a function of x, right? If I draw the arrow here like I did, well, y max is here. If I draw the arrow over here, well, then y max is going to be there. It's a function of x, right? And that function is given by this circular boundary. Solve that. This is x squared plus y squared equal to 1. Solve that for y. Y is obviously equal to 1 minus x squared square root plus or minus. I'm going to choose positive because y is always positive in this region of integration. So my y max is going to be 1 minus x squared square root. I step back and I make sure it makes sense. I'm integrating with respect to y, so my limits are either numbers or functions of x. And they are a number and a function of x. I should be good. Okay, then I'm going to integrate with respect to x. Y is gone. So I take this arrow and I sweep it through the region of integration starting at the minimum value of x where it first touches the region, and I sweep it in positive x direction to where it just leaves the region, and I ask myself at what x values are those arrows. The first one is obviously 0. The second one is obviously at a value of 1. It's the outer integral, so the limits have to be numbers. Can't be functions of anything. They got to be numbers. Okay, and now I'm ready to solve the integral. So I solve the inner one. That's going to be y cubed over 3, where y goes from 0 to 1 minus x squared square root. And then after that, I'm going to take the integral with respect to x. So you're going to end up with 1/3 integral from 0 to 1 of 1 minus x squared square root raised to the power of 3 dx. Okay, that starts to look like a complicated integral. But all is not lost just yet. We can use some sort of substitution whenever you're dealing with circles in some way, and wow, 1 minus x squared is kind of, y is equal to the square root of 1 minus x squared. That came from a circular equation. Whenever you're dealing with circles, your mind should automatically go to trig, sines and coses. Okay, when we parameterized the circle way back when in September, right? We parameterized it using sine and cos, trig functions, right? This is the unit circle. Even if it wasn't a radius of 1, you should still be thinking sine and cos, okay? So you could use a variable substitution here. You could say, well, I'm going to let x equal to the sine of u, which means dx is equal to cos u, du. Okay, x was going from 0 to 1, which means u is going to go from 0 to pi by 2. And I use that variable substitution. So now my integral becomes 1/3 0 to pi by 2 cos u cubed cos u du. Which, sorry, there's an s missing. Which looks a little bit better. Not a whole lot, though. We've got 1/3 0 to pi by 2 cos u to the 4th du. Now, that's not impossible. You can just look on the internet or you look in your math book at a table of integrals, and you'll find a formula for finding the integral of cos of something to some power, in this case, the 4th power. And you can apply that formula, and you'll get the answer, which happens to be pi by 16. Okay, I'm not going to write the formula, though, for finding cos to the n, the integral of cos to the n, because it's really long and kind of complicated, and we go, yuck, okay? Nasty integral. The problem is we have a region of integration which is circular in nature, and we're using rectangular or Cartesian coordinates, x and y. That's why we get this 1 minus x squared. Okay, but from the limits here. The function itself has nothing to do with it. It's the limits, because they're part of a circle, which are giving us this nasty integral. Okay, so this is a perfect justification for using a different coordinate system that is much more friendly to things that are circular in nature, and that is the polar coordinate system. Okay, so we're going to stop there. Don't come to me afterwards and ask, well, how did you do this? I'll just point you to the notes and say, look at that complicated formula, and if you have nothing else to do, figure it out. But no one would ever do that, because we have a far simpler way of solving this integral, okay? And that is using polar coordinates. And I believe you've probably run in polar coordinates already, right? You've run into them somewhere along the line in the last year and a bit. If not, just to remind you what polar coordinates are, they are two-dimensional coordinates. So, we're still dealing in the xy plane, but now instead of giving coordinates xy for a point like that in the xy plane, we're going to use r and theta, where r is the distance from the origin, and theta is the angle counterclockwise from the positive x-axis. So we're going to use r and theta as the polar coordinates for that point in the xy plane. And r is called the radius, and the origin is called the polar axis, and all these terms. Okay, this angle theta is sometimes called the azimuth. Okay, azimuth, when we're talking about positioning and navigation, we always talk about the azimuth. It's the angle from some axis. In mathematics, it's from the positive x-axis going counterclockwise. So a negative theta would be going, obviously, clockwise. Okay, we can relate r and theta to x and r. because we've got a right angle triangle. If we draw that, and we can use trig to do that, right? Theta is an angle in that right angle triangle. So x is simply equal to r cos theta, and y is equal to r sine theta. So for the rest of this course, those two equations need to be burned into your mind. You're going to use them, okay? They're simple. X is equal to r cos theta, y is equal to r sine theta. It's just trig from that right angle triangle. So now we can write curves in 2 dimensions using polar coordinates. For instance, what lecture are we in? We're still in double integrals. Yeah, so for instance, let's look at this one. Okay, there's a curve in 2 dimensions, right? But if you try to write the mathematical expression for that curve in x and y, it's very nasty. Whereas if you do it in r and theta, this is called a cardioid. And it's equal to r 1.5 minus 1.5 sine of 3 theta. Okay, so a relatively simple expression which is describing a relatively complicated 2-dimensional curve. Okay, so for curves like this, it's much easier to express them with polar coordinates than it would be for x and y. You can do it, but it just lends itself more easily to polar coordinates. Okay, so what does this have to do with double integrals? Well, when we're doing a double integral, we're integrating over some region R, a function of x and y, dA, where I've used dA before. That just means dx by dy, for instance, right? It's a small square patch in our region of integration. Okay, well, if we want to solve a double integral in polar coordinates instead, what do we got to do? Well, we've got to change a few things. We've got to change, first of all, our function. It can't be in terms of x and y anymore. It has to be in terms of r and theta. Okay, well, that's easy. We have equations, right? F of xy has to be transformed to f as a function of r and theta. Well, x is equal to r cos theta, and y is equal to r sine theta. So we just take our original function. Wherever there's an x, we substitute r cos theta. Wherever there's a y in this function, we substitute r sine theta. Simplify, we've got a function of r and theta. So that's one thing we got to do. We've got to change this function into a function of r and theta using these 2 equations. The next thing we got to do is we got to change the limits of integration, because we're no longer going to be integrating with respect to dx and dy. We're going to be integrating with respect to r and theta. So we don't need limits for x and y anymore. We need limits for r and theta. So we have to change the limits. Oops. And usually we're not given the limits for x and y, so we don't have to change them. We have to just figure out what the limits for r and theta are. Right? We will find those from the region of integration. The region of integration stays the same. Okay? Okay, and the final thing we have to do is ask, what is this dA? Well, if we're integrating with respect to x and y, dA is equal to dx by dy. But if we're integrating with respect to r and theta, it's not just going to be dr by d theta. We're not that lucky. Okay, so what are they? There's a couple of ways we can figure it out. I'm going to show you the second way later on at the end. The first way we can figure it out is, well, okay, let's just go back to this example, for instance, where our region of integration looked like this. Part of a circle. That's part of a circle, believe it or not. That's really bad. Let's try that again. Okay, let's say that's our region of integration again. Well, we're going to be integrating in the r and theta directions. So, you know, that means we're drawing a line kind of like this. And we're looking for dr and d theta, which means a small difference in r and a small difference in theta. Well, if I draw another circle like this, okay, then this gap here, that would be my dr. Or let's start with delta r. No, not small r. It's the polar coordinate r, right? It's the difference between a radius like this and a radius like that. Okay, I change r a little bit. Changing theta a little bit means, I'm going to draw it here. Okay, if this is my original theta, sorry, that's my original theta, right? Then this here is my delta theta. A little bit change in the angle. And that gives me a little patch of my region, right? It's this patch right here. It's a little rectangular patch. That is my dA, right? It's the small incremental area of a little patch in my region of integration. What are the dimensions of that thing? Well, I already, and if delta theta and delta r are small enough, this is basically a rectangle, okay? I mean, it is curved, but if you make these really small, this is basically a rectangle. So the dimensions of that are going to be this dimension times this dimension. Well, this dimension we know is delta r, right? So the dimensions of dA are going to be, again, I should have written delta A, but that's fine. Delta r, okay, and what are the dimensions of this side? Well, for a circle like this, with a really small angle in here, this dimension is basically this radius times this angle. Okay, this radius, let's call it r, this little angle, delta theta. Okay, so as I make these really small, the deltas becomes d, and my dA becomes r, dr, d theta. Okay, so now my integral, my double integral, is going to become, over the region r, f expressed in terms of r and theta, and dA, which is r, dr, d theta. Okay, that's my dA. So that's all we have to do. Okay? Okay, well, let's look at an example now of how we can find the limits. So we know what our double integral in polar coordinates looks like. We know how we can get there. Using x is equal to r cos theta and using y is equal to r sine theta, we can change our function of xy to a function of r theta, and then we just multiply that by r dr d theta all the time, okay? This r dr, this r here has nothing to do with this function. It's part of dA, so it's always there. Okay, r dr d theta times our function expressed in r and theta. Now we just got to find the limits. So let's look at how we can do that. Okay, finding the limits. Well, let's take a region of integration that looks like this. Again, we're in the xy plane, and our region of integration is going to be part of a circle again. If your region of integration is not circular in nature somehow, don't use polar coordinates. Use xy. But if the region is circular in nature, you should be thinking polar coordinates. It'll probably make your life a whole lot easier. Okay, so that's not a really good drawing, but this is the line. This is the line y is equal to the square root of 2 times x. No, square root of 2, not times x. It's a straight line, horizontal line, believe it or not. Okay, and this is part of the circle, x squared plus y squared is equal to 4. And our region of integration is in here. How would we find the limits for r and theta? Well, it's always good to know where all the terminal points of this region of integration are. We know that if I draw this line, this axis up a little higher like that, what is this point here? This point right there. Well, obviously x is equal to 0 there, and what is y equal to? What's y equal to at that point? Anybody else got another answer? I heard 2. This is the easy part. Obviously 2, right? Because it's part of the circle. And this circle has a radius of 2. Okay, so that point is 0, 2. What's this point down here? 0. Somebody other than him spit it out. Root 2, right? Okay, what about this point over here? What are its coordinates? Well, the y coordinate is easy, right? It's root 2. What's the x coordinate? Root 2? You got that from this equation, right? This point is part of this circle. So if y is equal to root 2, I've got 2 is equal to 4. X squared plus 2 is equal to 4, which means x must be root 2 as well. Okay? Okay, I got all the points. Okay. Now, we're looking for the limits for r and theta. So we're looking for r min, r max, theta min, and theta max. When you're using polar coordinates in a double integral, it's virtually guaranteed. There might be some reason not to do it this way, but pretty much every single time, you're going to integrate with respect to r first. It's just easier, usually, okay? So let's think that way. So we're going to integrate with respect to r, which means we hold theta constant, okay? And we're going to draw a line in the direction of increasing r. R always starts at the origin and goes outward, radially outward. That's what r means. It's the radius from the origin, okay? So if I pick some angle, say this angle right there, and I draw, and I'm going to keep theta constant, which means I draw r at that angle. So I draw r like that in the positive r direction, which means going out from the origin, and I draw it so it goes through my region of integration again. I would not pick an angle of theta like that, because then my r looks like that. It doesn't even go through the region of integration, useless. I pick a theta so that I draw the r so it goes through the region of integration, and I ask myself, at what value of r does it first enter the region of integration, and at what value of r does it leave the region of integration? Okay? Keeping in mind that, I could have drawn my r like this, or my arrow like that. So would r min be the same for both of those? Is this distance the same as this distance? Obviously not. So r min is going to vary. It's going to be a function of theta, right? This arrow has a value of theta like this. This arrow has a value of theta like that. They're different. So this r min is going to be a function of the theta I chose. Okay, so r min is going to be a function of theta. Okay, that's complicated. Let's do that after. What about r max? R max is this distance. And if I draw the arrow here, r max is that distance. Does that distance change? No, they're the same, right? What is this distance? Well, it's the radius of the circle, which is 2, right? This distance is 2, this distance is 2, this distance is 2. So that means my R max is a constant, it's 2. Okay, so that's easy. Okay, but what about R min? That starts to look a little complicated, because now we'd have to do something like this. Draw a right angle triangle. Can I get rid of this line here? No, won't let me get rid of it anymore. Okay, I'm dealing with this one though here. I'm dealing with this arrow here. Its theta looks like that. Okay, so now I have a right angle triangle. If I draw it by itself, it's going to look like this. Where this is theta, okay, and I'm looking for this R min. It's this distance here. I drew this triangle here. This is R min that I'm looking for. Okay, well, do I know anything else in this? Do I know this side of the triangle? Yes, I do. It's at a value of root 2, a y value of root 2, so this is root 2. So surely I can use basic trig now to calculate what R min is in terms of root 2 and theta, right? So when you do that, R min is equal to root 2 cosecant of theta. Just basic trig. Okay, so I got R min and R max that way. Okay, so I'm going to integrate with respect to R first. R is gone. Now I'm going to integrate with respect to theta. So I'm going to do the same thing. I'm going to take this arrow that I drew and I'm going to draw it so it just touches the region of integration at the lowest value of theta. That would be right here. Okay, that is going to give me theta min. And then I'm going to sweep that arrow through the region of integration. The tail of this arrow always stays at the origin. So when it just leaves the region of integration, it's going to be right there, right? That's going to give me theta max. Okay, so what's theta min? Now it's going to be this angle here. What is that angle? Well, this point here is root 2, which means this line, if I wrote an equation for this line, what would it be? Y equal to x. Right? The equation for this line here is y is equal to the x, because root 2 is on that line. Y is equal to x. It's a straight line that goes through the origin. So the equation for this would be y is equal to x. What's this angle? Pi over 4, 45 degrees, right? Pi over 4. Okay, what's theta max? Pi over 2, 90 degrees. Okay, there you go. There's your limits, okay? Notice again, we're going to integrate with respect to x first. So that means, so our integral over the region R is going to be we weren't told what the function is. We don't care here because we're not actually solving the integral. We're just setting it up, right? It's going to be R dr d theta, right? Where we're going to integrate with respect to R first. So R goes from root 2 cosecant theta to 2, and theta goes from pi by 4 to pi by 2. And then we solve the integral, okay? Any questions so far? Okay, so let's do a relatively simple example on that, where we're told the function we're integrating is equal to 1 minus x squared minus y squared, and our region of integration we are told is x squared plus y squared less than or equal to 1, x greater than equal to 0, y greater than equal to 0. It's the same region of integration we dealt with in the previous example where we used Cartesian coordinates and we got a really nasty integral. It's the same region of integration. It's that part of the circle which is in the first quadrant. Okay, that's our region of integration. Okay, well, the first thing we're going to do is we're going to convert our function from xy to r theta. So we get 1 minus x is equal to r cos theta squared minus y, which is r sine theta squared. Right? And if you simplify that, what do you get? You would get 1 minus r squared cos squared theta minus r squared sine squared theta, which is equal to 1 minus r squared cos squared theta plus sine squared theta. Cos squared theta plus sine squared theta is equal to 1, so you end up with 1 minus r squared is our function expressed in terms of r and theta. Okay, now I need r min, r max, theta min, and theta max. I'm going to integrate in the r direction first. So I draw a line through the region of integration from lowest value of r to highest value of r, something like that, in the positive direction of r. That is an arrow. Okay, at what value of r does that line enter the region of integration? R equal to, well, it enters right here, right? What's the value of r? What's the value of r right here at the origin? 0. So r min is 0. Okay, what's r max? Well, it's the radius of this circle, which is what? Square root of 1, or 1. So r min and r max are 1. This is we're going to integrate with respect to r first, so it's the inner integral. The limits either have to be numbers, which they are, or functions of the other variable, which are theta. Okay, but numbers are legit for the inner integral as well. Okay, theta min and theta max. Okay, I'm going to sweep this arrow through the region of integration from the smallest value of theta to the largest value of theta. The smallest value of theta is when I would draw it there. And then I'm going to sweep it in this direction until it leaves the region of integration, which is right there. Okay, theta min is what? Theta max is pi by 2, I heard. Exactly. So now my integral is going to be my function, which is 1 minus r squared, times dA, which is r dr d theta. Integrate with respect to r first. So the limits of the inner integral, r goes from 0 to 1, theta goes from 0 to pi by 2. Okay, so that is equal to r minus r cubed dr d theta which gives me 0 pi by 2 d theta, which gives me r squared over 2 minus r to the 4th over 4, right? Where r goes from 0 to 1. So I'm going to get 1/2 minus a quarter is a quarter, so I'm going to get a quarter outside here, 0 to pi by 2 d theta, which is just going to take the integral of d theta, I get theta, where theta goes from 0 to pi by 2, I get pi by 8. Pi by 2 times 1 over 4, which is pi by 8. Okay, so relatively simple integral. And if you would use the same region of integration from the previous example where we got that nasty integral, we had the same region of integration, but our function of xy was simply equal to y squared. And that gave us a nasty integral for the same region of integration as we just looked at, right? If we would use polar coordinates for that, well, this f r theta is simply going to be equal to r squared sine squared theta. So now if you do the integral, same region of integration, so the limits are the same as what we just did, but our function now is going to be r squared sine squared theta, r dr d theta. Okay, we end up with a much simpler integral. You're basically going to have to find the integral of sine squared. And sine squared, you can use the half-angle trig identity to convert that to cos of 2 theta, finding the integral of cos 2 theta. Much easier integral than before. Much easier integral. Be a good idea to solve this. Make sure you get the right answer. Okay, we will see you on Friday.